today is the third session of our lecture series on um, for this year. And today, our past chairman, Engineer Mrs. Kamala Gunawardena, Madam has joined with us. Actually, she initiated this lecture series 2 years back with Professor Sanjay Singh, and also our current chairman, Engineer Mangal Silva, is also there. Over to you, Madam.
Thank you, Engineer Vanduka, invited me to welcome the gathering. Good evening, everyone. I hope everyone can hear me.
Yes, we can.
Yeah.
We can hear you.
Actually, this is really an interesting forum for me because I have been working with this for last 2 sessions. So I really enjoy this working with this team. So this is after several gaps. Actually, I couldn't continue for the last 2 lessons. So I welcome first and foremost our resource person. Today, the well-known personality who needs no introduction and no need to say many things about our veteran and the distinguished professor, Tishan Jai Singh, Senior Professor of Civil Engineering at the University of Moratuwa. So I welcome you, sir, Professor Tishan Jai Singh. Also, let me welcome every one of you who has joined this lecture very anxiously. I can see a good number. So welcome every one of you for the lecture. Actually, let me just give a small note about what I like to say. This was actually your services, Professor, you contributed for as a resource person for 2 sessions, previous 2 sessions. It was actually really good stuff under the lecture series, Structural Design of Highway Bridges, previous session. And apart from that, for the previous one, you did about 20 lectures on high-rise buildings using Eurocodes online. And actually, it was winding up was a very physical, effective event. And it was so interesting and people were commending a lot. So with that, I think we are going to widen the session, recent advances in rich design technologies with Eurocode criteria was the last session, the last physical session. So that was very commendable, what I would like to say again. So it's a small brief with a very, very enthusiastic. I give this message to our members because I would like to request these members also to keep your momentum and make a good rhythm. So this lecture series would be a very, very interesting and a very effective one. At the end of the session, I think you all will be completing your very beautiful number. I mean, remarkable number, about like 80% or 90% of your attendance. So it would be a very important thing end of the session. So, Professor, I appreciate your commitment to undertake this series of lectures, and I can remember your willingness to conduct, I think, maybe around 28 or something for this session as well, right?
Yeah,
so,
maybe more than 25
with that,
lectures.
I invite Professor to comment the lecture on structural design of cost-effective lightweight hybrid multi-story buildings using Eurocode number 3. I'm correct, no?
No, 2. Eurocode 2, please.
Eurocode 2. Correction. Thank you. I greatly appreciate your acceptance for this session under the chairmanship of our dynamic engineer, Engineer Mangal Silva. So he's around today. So we are starting today's event right now, and it's an honor for me to do this instigating note actually. So over to you, Professor. Thank you.
Thank you very much, Madam. Professor, I'm also here, so please continue.
Yeah.
Thank you.
Okay, Mangala. Now you all can see the sheet, right?
Yeah, we can see, sir.
Yeah. Just give me one second until I open. Yeah, now it's all done. Right, whatever extra we need, we'll open later. Today we are going to talk about. Can you all hear me properly?
Yes, sir. We can hear you.
Yeah, we can hear.
Yeah. Okay. So today we are going to start talking about use of reinforced concrete. Because last two sessions we talked about how to make concrete. Now today we are going to talk about how to use reinforced concrete. So what is the first thing? The first thing, the fundamentally. Now we are inserting steel in concrete. Now what is the reason for these two to behave together? The important thing is coefficient of thermal expansion of steel is concrete is about 10 into 10 to the power minus 6. Steel it's about 12 into 10 to the minus 6. So the coefficient of expansion are more or less the same. The coefficient of expansion, the values are more or less the same. So that's why we can use a material called reinforced concrete. So that's a very important thing. Then, so today is 13th, 2023, Civil Engineering Sectional Committee, lecture 3, page 1. So that's the first thing you have to keep in mind. They are having a similar coefficient of thermal expansion. Because of that reason, we can use concrete and reinforcement together. Now let's look at what we know, what all of you know. That is BS 8110 stress blocks. So that is part 1. I will use 1985 because 1997 code is only a minor variation. So it's very easy to talk in terms of 1985 code. And anyway, we are not going to use it. So I will use the earlier one. Stress strain curve for concrete goes like that. And the maximum strain allowed is 3.6. This value is very important value. And here elastic, and then it goes into plastic. And here we have a magic number, and so we have to see what is the magic number that we get here. So what we do is we test the Q. British standard, we test the Q. This 150 millimeter, 150 and 150. And how do we test it? We test it between two steel plates, the thick steel plates, what you call steel platens. So what happens is when you are applying the load, when you apply sigma, what happens is you get nu times sigma here. That is the Poisson's ratio. So with that, what you get is there will be microcracks forming, and finally the cube should break like this after the formation of microcracks. Is it clear, Mangala?
Yes, sir.
It's all clear, is that right?
Yes, sir.
Yeah. So then what happens is, now these plates, because this height is only 150, this height is only 150, these plates will restrain this concrete. So finally we say stress is equal to force divided by area. So the stress that you calculate this way, when we say 20 megapascal concrete, so 25 or 30 megapascal concrete, we'll use 30 megapascal because it's now many engineers use 30 megapascal. The reason is it gives a better durability, and I explained you how to improve it even further by using fly ash earlier. Right. So what happens is we use 30 megapascal. Then the actual strength of concrete, here you get 30. The actual strength of concrete is 30 multiplied by 0.8. 30 multiplied by 0.8. Then the other thing is we are testing the steel, the concrete in compression. But when you are using, we are using it in flexure. So here you get compression. And this compression is flexure, caused by flexure. MOI is equal to sigma y type of thing, initial. But in reinforced concrete, the behavior is different because we say below the neutral axis, concrete is cracked. So because of that reason, we get this and this. And if you if you look at the stress strain curve going like this, so what happens is gradually it will become like this, and we say rectangular parabolic. And in BS standards, we said this is equal to rectangular with a depth of 0.9x. So that's what we said in the British standards. So this is number 2. So I'm going to a new page now. This is Civil Engineering Sectional Committee. Lecture 3. Page number 2. Is there any question you'd like to ask here? This is a simple theory. So we say, because we are using like this, the actual stress is 0.85 times the actual strength, 30 multiplied by 0.8. So you can multiply 0.85 and 0.8 together. Multiply 0.8, 5 and 0.8. When you multiply 0.85 by 0.8, what is the answer? 0.67. So we say 68. We say the strength of concrete here in the stress strain curve is 0.67 times FCU, cube strength, FCU. So if I mark here, this value will be 0.67 times FCU. So that's how you get 0.67. Then what it says, the partial factor of safety for material strength of concrete is 1.5. So divided by 1.5. Then you get 0.45 FC. So if you are designing a column, although we say column is maybe axially loaded, although we say the column may be axially loaded, so this Civil Engineering Sectional Committee, lecture 3, right? So if you say although the column is axially loaded, there will be a minimum moment that you have to consider due to 0.5%, due to 5% excess of the load. So because of that, we say the load carrying capacity N of a column is 0.45 times FCU. Now you know how you get 0.45 times FCU, that is 0.67 times FCU divided by 1.5 multiplied by area of concrete. So the load carrying capacity of a column is 0.45 times FCU multiplied by AC. But we can't construct a column without any reinforcement. The reason is, there can be cracks. Due to thermal movement and or other restraints, there can be cracks. So we are supposed to provide the minimum percentage of reinforcement, 0.4%. So we say whatever the percentage, the area of reinforcement is. Then we have to make sure we take into account what the steel can carry. That is Fy AS, the area of steel in compression. So we can say AC, area of steel in compression, and Fy, why we get 0.87 is the reinforcement can be either in compression or tension, and because it's manufactured under factory conditions, we divide by 1.15 factor of safety, and you get 0.87 times. So steel, whatever the strength specified by the factory is the strength. But we have to have some factor of safety. We have a small factor of safety, 1.15. So now you can see, now we must get this strength. And how are we going to get that strength? What we do is we have to cure the concrete. Once you pour concrete, the strength is 0. After 1 day, you get 10% of the strength, so that we can remove the shutters. What many people do in Sri Lanka, after that they think now it's hard, nothing to worry. They don't cure sufficient. Very few people pay enough attention. But I showed you why curing is important, because we have to continue this strength development process, number 1. Secondly, when you cure, there will be a lot of hydration taking place in the cover zone, and we will end up with the cover without voids, because calcium hydroxide generated will have a higher volume than the original cement particles. So all these materials that are reacting will have some higher volume, but they are not hard materials. So whatever the spaces available will be occupied by whatever these extra materials. And that way concrete can become denser. Dense concrete will not carbonate easily, and you can get a structure lasting a long time once you cure it. On one side, it will be strong. On the other side, it will be durable. So when you are using reinforced concrete, make sure minimum of 7 days of curing is essential. I mean, if you can do little more, it's even better. By at least keep it moist. But keeping it extremely moist for 7 days is essential. But in many sites in Sri Lanka, we can't see this type of attention paid to cure. Bandhuko, what's your suggestion, or Mangala? What do you think?
Yes.
I mean,
Yes, sir.
it's not easy to.
Hello, sir.
It is not easy to persuade people to continue curing for 7 days. Very
Yeah,
difficult.
it's very difficult, sir.
Yeah, but they have to understand, because all our calculations are correct. Not at the 20% or 30% strength. Our calculations will be correct if we cure it and achieve the desirable strength. And for that, the modern cements needs about 7 days of curing. Modern cements need about 7 days of curing. That's why we are proposing that we use at least 10 to 20% fly ash. Minimum of 10% fly ash will make sure there's enough material in it. So whatever the calcium hydroxide is produced, the reactions can take place later, gradually, where the fly ash starts reacting with whatever the calcium hydroxide produced as a result of curing process. So if you look at the attitude of the people, and I was looking at Hilton Hotel recently, which was built over 40 years ago. The specification said, cure the concrete for 1 month. Cure the concrete for 1 month. So after 40 years, we looked at the carbonation. Carbonation is very small. The maximum carbonation after 40 years of existence was 10 millimeters. Some places it's even 2-3 millimeters. Why? Because Japanese construction, and when they say we cure for 1 month, they cure for 1 month. They will not try to find shortcuts. And they never used curing compound. They used water, cured the structure. Now, 4 years afterwards, we took course. We could not take course, but fortunately, for some other repair work, they had to drill through the slabs. So we used those samples, checked for carbonation, and we found some places the carbonation can be only 1 millimeter or less, whereas some places the carbonation maximum could be about 10 millimeters. So what do you think about that kind of results? And you can see the strength, the importance of carbonation. So the importance of curing in reducing the carbonation. So I'm sure if we if we are allowed to take more samples, we would have found the average carbonation, that is penetration of the low pH regime into the concrete due to carbon dioxide penetration or absorption. It would be in the range of 3 to 5 millimeters, which means a well-constructed structure like Hilton Hotel will have a lifespan maybe in the range of 150 to 200 years. But based on our limited resource, we said without any fear, it will have a trouble-free service for another 35 years. Because for any investor, 35 years is a long enough period to make decisions. So whether to invest or not. So, but my gut feeling is this hotel will not have any issue if looked after properly with adequate waterproofing on the exposed areas. The lifespan of this hotel, because most of the places it's all covered, no adverse effect except the carbonation. This hotel can easily last 150 to 200 years. That's the way we have to do construction. But unfortunately, what we see today is, recently we have visited one school building, maybe 15 years old, but already columns have started deterioration. One is poor quality concrete with very little aggregates. Second, they are not cured. They have cured everything else except the columns. Whereas we have to understand column is the key parameter or key element in a building, and column is the one that is heavily loaded. So it has a small cross section and a heavy load. You must pay a lot of attention to columns, and I'm going to show you why poorly constructed columns are standing. But that is not a good way of constructing. Curing must be paid a lot of attention, and I have seen young engineers are also responsible. They are reluctant to implement curing adequately, even if it's an uphill battle in the industry to cure concrete. But it should not be the case. We should be fully aware curing is important. Is there any problem?
No, madam. No, sir.
Video.
I think sir
BLPS
didn't write anything for longer period, so it's like not working the video. I think it is not like that.
No, it's working. You can see.
Yes, sir.
Yeah, it's working, right? Right. Okay. So basically, I was talking a bit because this is very important, because we have to change the attitude of the engineers as well. But fortunately, in the modern concretes, if you add about 10% fly ash with 7 days of curing, we can achieve very significant level of expected strength. Right. So now we have a simple equation. So what is the equation? N is equal to this 0.45 FCU AC plus 0.87 FI AC. And then we say, if you are going to use this equation, don't use it that way. Reduce the capacity by 10%. So that means you get 0.4 FCU AC plus 0.75 FY AC. And then if you are going to design a column, considering that there will be a moment, but the spans on either side on the column are having similar values, so the maximum variation is 15%, then you don't have to do anything. You can simply design the column by using don't do any calculation. N is equal to 0.35 FCU AC plus 0.67 FI AC. So if the moments are going to be small, just write one equation, and that equation is a 10% reduction. So N is equal to 0.35 FCU AC plus 0.67 FI AC. That is ceiling. So what you have to do is take the column, find the steel area. Steel area is concrete area AC is equal to A multiplied by AC. So if you want, you can substitute that way. Otherwise, some people just ignore it because already we have reduced, and the steel ratio will be about 0.4 to 1%. Right. So in a column, what is the amount of steel we have to produce? We have to provide. This page. What is the amount of steel we have to provide? Amount of steel is 0.4%. If the column is lightly loaded, so in a 2-story, 3-story, 4-story building, you can provide 1%, 4.4%. But if it's a tall building, we cannot say it's a lightly loaded, it's heavily loaded. Then you have to provide 1%. So any column that you suspect that it is heavily loaded, you have to use 1%. So that is why when you are doing the piles, we know piles are very lightly loaded. So we can provide about 0.7%, even 0.6% might do, because what is needed minimum is 0.5%. Right. So in a pile, the minimum need is 0.5%. You can provide anything above that. So in Sri Lanka, often we provide 0.7 to 0.8%. 0.7 to 0.8%. So now you can see why we have these values. Pile has a massive area, and under working stresses, we say the stress on concrete is 0.25 times FCU. So it is lightly loaded, 0.25 times FCU. So the pile needs only about 0.5% reinforcement. To be on the safe side, and also to make sure the reinforcement cage is sufficiently strong. Generally, many engineers like to use about 0.7% reinforcement, but even if you drop it to 0.6%, it's not going to be any problem. But then you might ask, well, what is going to happen due to earthquakes? So in the earthquake, what matters is not the longitudinal reinforcement, what matters is the spiral. So in a pile with a pile cap, where the hinge occurs here. So in this area, you have to have confinement. So start seeing here, you have to have confinement. So generally, it's a good thing to have T10 at 100 centimeters, the spine. But when you are going here, no problem. No plastic hinges. So you can easily go for 150 spacing, because too much spacing is also sometimes detrimental. But if the experienced piling contractors might use even 200. But too much space is also detrimental, because when you are doing the piling operation, you need a strong reinforcement cage. So the piling operators, the piling contractors will tell you whether they can manage with 150, or you can allow you to increase it to 200. But at the top of the pile, for about 1 meter, we need to have high degree of confinement by having 10 millimeter bars at 100 center to center on a spiral, because spirals have a huge confining capacity, not like rectangular reinforcement. So the whole idea is, by having this confining reinforcement, what we are doing is, we are applying a load here, but we are applying a load these ways also. So there's a spiral to confine, and so when you apply this load, there will be stress this way, mu times sigma. But due to the spiral, there's a huge confinement. So what happens is, the behavior of concrete will not be like this, that is unconfined. The behavior of concrete will be like this. So you can see there's a huge area under the concrete stress strain curve, and that gives the ductility. So in the case of piles, what we need is ductility, or ability of the pile to absorb energy. And how we achieve that is not by increasing the vertical reinforcement, but by increasing the confinement. So that's why we like to have T10 spiral at 100 millimeter centers. And if you look at any typical bridge detail, you'll find the engineers have used T10 bars at 100 center to center at the top part of the pile, and that is to make sure the top part of the pile has concrete that is confined a lot, so that it will not disintegrate easily, because there's a huge strength in concrete when you have a 3-dimensional stress state, like the way that you do triaxial tests in soil mechanics. Once you apply the stresses in all directions, all as compressive, then the compressive strength of the concrete, 30 megapascal concrete that you use, will not be 30, it can be 45. And that comes not because the concrete is strong, but the confinement is high. So that's how we prevent earthquake damage on piles. So in Sri Lanka, because it's a low seismic country, piles can be constructed with 0.5% reinforcement onwards. So it's up to the design engineer to decide whether you use 0.6%, 0.7%, or 0.8%. So it's totally up to the structural engineer. And again, if you look at piles, so because I'm talking about compression members, one of the key compression members will be piles. So what happens is, in the case of a pile, so this is the pile, and if you look, it is subjected to, say, 7.5 newtons per millimeter squared, or 7.5 megapascal stress. So 1 megapascal is equal to 1 newton per millimeter squared. So what is the stress condition? So we have 7.5. And then if there's a bending moment on it, generally you don't get a big bending moment, you get a small bending moment. And then what happens? It will give a stress diagram like this. So what is the resulting stress diagram? This. Now, these are all in compression. If the whole thing is in compression, why do you need reinforcement? You don't need reinforcement. So because of that reason, when you have a long pile, 30 meters, and if the soil is good, laterite, so the confinement is good, there here you can have something like clay sand. So when Professor B.L. Denacon taught us piles, he said 6 meters of reinforcement. But you don't have to be, you can be little lenient on it. So you might say either 9 meters or 12 meters of reinforcement. And unless the pile is in tension, you need only 9 meters or 12 meters of reinforcement. If the pile is going into tension, then you will need more. But if the pile is going into tension, there's something wrong with your design. So because of that reason, I will show you later how to deal with this pile going into tension and or how to ensure that the pile does not go into tension. For that, you have to actually work with the architect and make sure the shear walls are loaded. So if the shear wall is loaded, shear wall will never go into tension. If the shear wall doesn't go into tension, you can't have pile going into tension. So you have a wall, pile cap, piles. If the whole wall is in compression, can you have a situation where the pile is in tension? No. So you have, when you are selecting the superstructure, you have to be mindful about the pile foundation and select. So I am explaining these things today with piles, which is a topic generally we teach at last. Is you can clearly see pile is a member in column in compression, subject to a very small bending moment. Then you might ask, okay, why the pile is subjected to a small bending moment? The reason is pile is connected with a pile cap, and then there will be ground beams above the pile cap. So this is a ground beam. So when you have a very heavy member at the top as a beam, then the pile will be subjected to very small bending moments. And I will later show you these piles can easily take any moment up to 500 kilonewton meters, or it can go up to about 800 kilonewton meters. If the pile diameter is about 1.2 meters, the pile can easily take a bending moment of 800 kilonewton meters when you provide minimum of 0.5% reinforcement. So as long as piles are concerned, if somebody says we need a lot of reinforcement, it is wrong. We need some reinforcement to make sure the piling, the reinforcement used, the cage, reinforcement cage that we use is strong enough to be handled, because we have to lift it, lower it, we are doing a lot of things, and because the reinforcement is not that important, and also because we are using QST reinforcement, what we call QT bars, quenched and self-tempered, these bars can be welded without losing strength. So you can use welding and make sure the cage is strong. The reason is, the reinforcement is not important. We need some reinforcement as a precautionary measure, but piles have a very high moment capacity arising due to the fact pile is in compression. So in that case, what is important when you are constructing a pile? What is important is verticality. What is important is verticality. So that's the place where you need attention, not on how you place the reinforcement cage or what. So what is important is verticality. Right? So when you are doing the piling, pay maximum attention to assure that the pile is cast vertically. That is it. So that's why we recommend the use of temporary casing in the top part of the pile, so that we'll have a better control if the soil is weak. If the soil is weak, we strongly recommend the use of temporary casing, and most of the piling contractors might say, oh, we can easily do 6 meters of temporary casing, and generally they are very comfortable with 8 meters of temporary casing. With some little difficulty, they can go up to about 10 or 12 meters. But I prefer something range like 8 meters, because when the temporary casing is withdrawn, if the soil is very weak, I would like about 8 meters. But if the soil is strong, but you want to minimize the bulging and withdraw, have a temporary casing, then you can even go up to 10 or 12 meters. But if the soil is weak, then when you are withdrawing, the concrete may not have enough strength to hold it properly. So because of all these reasons, 6 to 8 meters of temporary casing is highly recommended in weak soil conditions, whereas in stronger soil conditions, where the SPT values are low but they are not extremely low, then you can have even 10 or 12 meters of temporary casing. The whole idea is, by the time the casing is withdrawn, concrete should have sufficient strength to hold it on its own. So if the soil is extremely weak, then better to make it shorter, because the reason is the weight of the concrete in the shaft. But whereas if it is reasonable soil, but you like to have like clay soils, where you like to have some confinement to ensure that the amount of extra concrete needed due to bulging can be kept as low as possible, then you can even go for up to 12 meters of temporary casing, or it can be even some situations with little difficulty, piling contractors might agree, okay, I'll do 14 meters of temporary casing, but generally 12 is the range that we generally consider as maximum. So these are very important practical information, because we are talking about a column, and one classic application of a column is a pile. So, and in pile, there are a lot of opinions, because we don't see the pile. So, but how we make a good high quality pile is using temporary casings. And the moment you use a temporary casing in the upper part, which can be subjected to moment, what we need is a kind of a minimum reinforcement of about 0.5%. But it's customary in Sri Lanka to use 0.6, 0.7 to 0.8% reinforcement in the top part of the pile, because the reinforcement cage also needs some stiffness. And the most important thing in the pile is having a spiral providing confinement to concrete at the top part, because we like to have triaxial stress state to assure that concrete will not crush under earthquake situations. And then as we go, after about 9 meters or 12 meters, theoretically you don't need reinforcement. If you are providing any reinforcement, provide only 0.5%, because anything more is useless. You are not going to gain anything by providing more reinforcement. And also the other important thing is, if you are curtailing the reinforcement, you are not going to lose anything. And I can tell you, the tallest building in Sri Lanka, that is Altea, twin towers, 168 floors, 164 floors. The length of the reinforcement cage is only 12 meters. The length of the reinforcement cage is only 12 meters, because it has good sandy soil or weathered soil, weathered rock above highly fractured rock. So in the highly fractured rock, the original design was key to use only one 12-meter length of reinforcement to reduce the cost of construction. And I have spoken to many piling experts, real experts. They say the one length of reinforcement, maybe 6, 9 or 12 is generally sufficient. And I prefer something like 9 to 12 rather than 6 because, we have to allow for some, moments. Sometimes the moments can be there up to about 4 meters. Again, the other important thing that you have to keep in mind is in a pile, the moment is will be only the first 3 to 4 meters of the pile. After that, moment is very low value, almost negligible. And with a model on SAP 2000, where I can show you by representing the soil as springs, the bending moment rapidly reduces to a value close to 0. I'll show it later today, and you can remind me when we start modeling, or when I start showing you how to do modeling, just remind me how to model the soil when it is sandy and how to model the soil when it is clay. So I will show you all these different variations, but keep in mind that the bending moment in a pile supporting a pile cap, and when the ground beam is present, generally the moment vanishes to a value close to 0 within 3 to 4 meters. So that is some very useful information, and that is the area that we need extra confinement that we provide by having a spiral at close spacing like 100 millimeter, but we can relax it as we go down. And then even if you don't have any reinforcement, nothing will happen because it's like a pre-stressed concrete member having a high stress. So for all this to happen, the most important consideration is pile must be as vertical as possible. Pile should not be inclined, but these days in Sri Lanka, most of the contractors use BG24, BG25, 26, 28, 30 type machines. And those machines are very hardy machines. And these machines, the experienced operators can very easily maintain the verticality. So they are used to it. So the risks are low because we have good operators and also piling contractors. Also, these machines are very versatile machines, high capacity machines. So it's possible that we can easily construct a pile which is vertical. So verticality is important, but we can actually make it vertical. So that is some extra information. And you might ask why I talk about piling. The reason is, now gradually we are coming out of the kind of very serious situation in the country. And so when we are, the first thing that will happen is piling. But because we are coming out of a downturn, the material costs are very high. So everything must be saved. So the first thing that we can save money is piling. And we must make sure that we know the theory well. And the theory is, it's a column. And a column subjected to uniform stress is like a pre-stressed concrete member, very strong in carrying flexure. So we don't need reinforcement to carry flexural moments in a pile. Two reasons. One is the bending moments will vanish in the first 3 to 4 meters of the length. Secondly, in a pre-stressed member, even without reinforcement, it can carry a big bending moment provided the pile is vertical. So those are the reasons. Banduka, is that clear?
Yes, sir. That is clear.
So yes, it's clear. Very clear.
Yeah, it's clear. Right. Good. So basically by using, showing a small example of how to design a column, now we have gone, I have provided a lot of information on piling, because any new project, the first thing is piling. So think about optimizing the pile by using all these different methods, right? So now we'll so we have this equation. Now let's see how we get the same equation in Eurocode, the comparable equation in Eurocode. The comparable equation in Eurocode. So now I'm going to derive the same equation using Eurocode. Is it okay?
Yes,
So
yes,
now
sir.
I'm
Please
going to
continue.
Eurocode.
Please continue, sir.
Yeah,
Yes.
yeah. If you have any difficulty in hearing or anything, please let me know.
Okay.
Right. So now Eurocode. C 25, 30. So earlier we are talking about 30 megapascal concrete. Now we are using cylinders, 150 millimeter circular, 300 millimeter, and we place it under the plates, and so here no confinement. So what you get is actual. So what you get as strength is actual. Then we have to say, okay, now we test this way, we use this way. So we have to need 0.85 factor. And then we need 1.5 partial factor of safety, right? Partial factor of safety. And as engineers, you should never say factor of safety. It's partial factor of safety. The reason is, if factor of safety is overall factor of safety. But we are not having an overall factor of safety. We are putting the factor of safety only on the material, so it has to be partial. It's very important that the engineers use the correct terminology. What is the answer? 0.567. So if you are using Eurocode, N is equal to 0.567 FCK. Now in Eurocode, the cylinder strength is FCK multiplied by area of concrete plus 0.87 Fy AC. So you can use any notation that you like, but if you look at Eurocode, it's using FCK, YK, and all those notations. Now 10% reduction. So 10% reduction is 0.567 multiplied by 0.9. So you can say 0.5 FCK AC plus 0.75 FYK AC. And if you want, you can have a further 10% reduction. So multiplied by 0.9 again. So you get 0.45 FCK AC plus 0.67 FYK AC. So I get an equation like that. So even on the Eurocode, code doesn't give the equation, whereas BS code gives the equation. So we can use BS code approach, where you have a beam supported by a column, and this side 7 meters, this side 6 meters. So what is the difference? 6 divided by 7. So it is 15% difference. So the chances are that the moments are very small. So if you are in a hurry, you don't have access to a chart, the spans are almost equal, just use this equation and find the reinforcement. So for example, let's say we have a column that we expect. So this is how you work it out. Generally, say we have a little easier question. So we have one-way steps, and this side 7 meters, this side 6 meters, and here you get a column. So steps are like that, right? So the load on the beam is from this place to this place. That's the load on the beam. And so we like to get the loading on the column. And so how do you find the loading on the column? These 7 meters, 6 meters on this side. So we have to find 1.35 GK plus 1.5 QK to find the load. So there are some magic numbers for this. For a house, this value is 8 for a house. Then for an office building, office building, it can be 10 to 11 kilonewtons per meter square for an office building. And if it is an, an auditorium, we say about 13 kilonewtons per meter square auditorium. Now, what is the value of these numbers? Now, I don't do any calculation. Let's say this is an office building. So I simply use 11 kilonewtons per meter square. So 11 into 3.5 plus 11 into 6, 11 into 3. That is the load. 11 into 3.5, but this way we say these beams are at 4 meters. So we have to multiply it by 4. We also multiply by 4. So the load from the floor will be, now I have not done any calculation because I have some rules of thumb. So for an office building, I expect the design load to be around 11 kilonewtons per meter square. But for a house, I would expect something like 8 to 9. And this will include the weight of the beam as well. So when you use these numbers, so what I do is I don't do any calculation to find the exact loading because I know some numbers and straight away I find the beams are spaced as 4 meters. So 4 meters of load will come onto this and the load is 11 and so the load on the beam is 44 kilonewtons per meter over length of 3.5 meters because there's a span of 7 meters. So I get 154 here and 11 multiplied by 3 multiplied by 4. So I get 132 from this side. So the load is 154 plus 132. So from this flow, I am getting a load of 286. And let's say I'm doing a 10-story building having a grid like this. The grid is on one side you get 7 meters, the edge spans are 6 meters, and the beams are located every 4 meters, and they have been designed as one-way steps. So just to make things simpler, right? They say they have been designed as one-way steps because in some other places you will get 8-meter spans as well. So the design has decided, okay, I'm going to design everything as one way. 6, 7. Right. So now 286 load comes from one floor. And let's say we are in a 10-story building. And so there are 10 floors. And we are going to design the most critically loaded one. So there are 9 floors above. And I'm going to design the column at the ground level. So 9 floors above means 286 into 9 is the load from above. And that gives into 9, 2574 kilonewtons. So I have to find the reinforcement for carrying 2574. But you can see the bending moment is very small because both sides are fully loaded. Both sides are fully loaded. So if both sides are fully loaded, the columns will cancel out at the column. So I'm going to say, okay, the load on the column is 2574 kilonewtons. Now comes the important question. Right. What is the size of the column that we need? Now, would it depend on axial load or earthquake resistance? Now, which is governing? This or this? Or both? Yes, it's both, but the earthquake resistance is more important. So you can see we are having spans like 7 meters. So what is the section of the column? Beam. So section is likely to be 600 by 350. 350 is to make sure that there's enough width in the beam to place the reinforcement. So I don't generally like very thin beams unless there's a special reason to do so. I like fairly wide beams like 300 or 350 wide beams. I don't like 250 wide beams. It was very difficult to do the construction. And we need little, and anyway, beam is an important member. Why do you want to make it so thin? If you want to make something thin, what is the member that you will use? Slabs. You will try and make slabs as thin as possible, but you will be generous with the columns. So if this is the case, what is the minimum size of the column that you use? Minimum size of the column has to be 500 by 500. Or preferably even larger, 600 by 600. Why? That's where the earthquake resistance comes. So we have this, every floor, these beams, the beams and columns. Now, in a portal frame, where do you get the hinges forming? Weaker member. Or it could be here. Which is better? This A, this B. Which hinge is better? B is better. Why? If the hinges form on columns, columns can give away. That means they can just be flattened. The whole building will be flattened by the way. But if the hinges are forming in the beam, then it will convert the continuous beam to a simply supported beam. Now, can we have a multi-story building with simply supported beams? Yes. And there are certain car parks where they have used precast beams and the beams are simply supported. We don't have any problem. So what it says is, we can have the precast beams and make it simply supported. So if you have a plastic hinge forming in the beam, it will convert the continuous beam to a simply supported one after a certain moment. So we like all the hinges forming where? We like all the hinges coming in the beam, and we know the weaker member will be forming the hinges. So where do you like? What is the size you like? You like a column larger than the beam. You like a column larger than the beam. So let's assume, based on this information, we have selected 500 by 500 column, because 500 by 500 column is fairly large and it is larger than 600 by 300 B. So the hinges will definitely form on the column, on the beams. So now we have a column size. Now, can you see how I arrived at the column size? It is not based on the carrying capacity. It is based on the earthquake resistance. So I have a column now having 500 by 500 carrying a load of 2574 kilonewtons. And so I say N is equal to point, the equation is 0.45 FCK AC plus 0.67 FYK AC. So I'm going to say, I'm not going to find any reinforcement. So I'm going to say 2574 into 10 to the power 3 is equal to 0.45 multiplied by 25, and that is A minus ASC plus 0.67 times 500 is the strength of steel multiplied by AC. And A is 500 by 500. So we are interested in finding the amount of reinforcement. So we are going to say 2574 into 10 to the power 3 minus 0.45 into 25 into 500 by 500, because now the column size has been selected based on the earthquake criterion, and that is equal to 0.67 multiplied by 500 minus 0.45 times 25 times SAC, and from this we can get the answer. So the answer is we get AC as, sometimes I might get a negative value, that means I don't need reinforcement. That can happen, then I provide the minimum reinforcement, or because this is a 10-story building, I'll provide 1% reinforcement. So we get 2574 minus 0.45 into 25 multiplied by 500 multiplied by 500, and as I told you, I am getting a negative answer. Divided by whatever comes here, it doesn't matter. So I will calculate that also. 0.67 multiplied by 500 minus 0.45 multiplied by 25. So that is 323.75. I'm getting a negative answer. That means no design reinforcement. But because it is a 10-story building, I'm going to point 1% reinforcement. That means 500 into 500 into 500 into 500 into 0.01. So the reinforcement will be 500 into 500 into 0.01. So I get 2500 millimeters squared of reinforcement. So the amount of reinforcement, I'm providing 1% reinforcement because that's a heavily loaded column, because we are designing a column in a 10-story building. So what I do is I will see. So if I'm going to use 16 millimeter bars, the area is 201. So what I can do is I can divide this by 201, and I will need about 14 bars. And because I am deliberately providing, I can even provide 12 bars. Slightly less than 1%, but it's okay, very close to 1%. So what I can do is 16 millimeter bars. I need 12 bars. So if I provide 4 on one side, 4 on the other side, 8, and I can provide 2 there, 2 there. Now comes the important question. Now we are concerned about earthquake resistance. And how do we assure ductility in these schemes? In this one, how do you assure ducting? So the hinges again, if they ever form, now we have made sure the hinges will not form, but if a hinge ever forms, where would it form? There. Hinge will form there. So how could I make it strong? So what I do is I will have one link going right round and 8 millimeter diameter. We call it now it is H8, not T8, H8, because we are dealing with Eurocode. So the moment you are dealing with Eurocode, you have to change the numbers. And I will provide one link here and another link here. So that is the arrangement. Why? I like confinement for concrete. The best way to provide confinement for concrete, sorry, there's some comments, so I will answer those again. So basically, I like to have confinement. Why? Confinement can, so we confine the concrete in all directions. The strength is very high. Strength is very high. So we confine the concrete. So we provide something like 100 millimeter center to center H8 bars for about 0.6 meters. Then I relax it to about 12 times diameters for about another 1 meter. And the remaining part I can go up to 10 times diameters. Because there's no way the center of the column can fail. So I can go up to about 20 times diameters. But I like something like 100 millimeter center to center at the top, at the bottom, over a length of about 0.6 meters. And the other important thing I like is, these are reinforcement, some additional reinforcement in the column going in both directions within the beam, so that inside the beam also we have some kind of confinement. Otherwise what happens is, this is perfect but it fails here. It fails here. To prevent that failure, what we do is we have a junction. So we provide some reinforcement because this is the beam reinforcement. Anyway, there will be other reinforcement going that way. But within the middle portion, because this can be about 600 millimeters deep, in the middle, we'll have some additional reinforcement going like that. And those are just maybe 12 millimeter bars. You don't need 16 millimeter bars, just 12 millimeter bars. Why? The moment you put some reinforcement inside the joint, any kind of stress reversal that occurs during an earthquake can be easily resisted. So what we do is we use H8 bars, then we use H12 bars in the middle of the joint, so that those are additional bars tied to the side of the beam. So beam is like this. We have some top bars, bottom bars, and we'll have some side bars like this, and some side bars going like this. So the idea is, we need better confinement. We need better confinement. So what we do is we provide these additional bars of 12 millimeter H12 and create a situation where the joint, inside the joint also we have reinforcement, not at the outer boundaries of the joint. Inside the joint also we have some nominal reinforcement, and these nominal reinforcements can ensure a building detailed this way in Sri Lanka will never suffer any damage in an earthquake. That's the way that we can prevent, because what we are doing is, by confining the concrete, we are increasing the strength of concrete. So when the biggest problem in an earthquake is this concrete disintegrate. So the biggest problem is this will break, because this will be subject to tension. Those will break into small pieces, and not to the aggregate level, but bigger pieces. And the moment the concrete is crushed by breaking into bigger pieces, this crushing occurs not due to concrete compression, but due to tension. So to prevent those tension in concrete, so first thing is we enhance the confinement. So the tensile stresses would be lower, and also we'll make sure within the joint also we enhance this confinement, or we provide some flexural reinforcement that can carry any kind of tension. So the whole idea is improve the ductility. A ductile structure cannot suffer significant damage during a 20-second earthquake. Now, why do I say that? Why do I say 20-second earthquake? So the reason is 7, 8. We are not in a plate bound area, so the energy absorbed will be small, and now here you have the ring of fire. The energy is massive, so the earthquake can last 1 minute to 5 minutes. Those are massive earthquakes. But here we are within the plate. These over 1,000 miles, 1,000 kilometers away. Ring of fire is about 1,400 kilometers away. So whatever happens there can create a tsunami, but not felt by tsunami. But what we get is intraplate, and our faults are not significant enough to create an earthquake lasting more than 20 seconds. So if you look at the natural period of vibration of a 10-story building is 1 second. So how many cycles that the building will undergo before the earthquake ends? Maximum of 20. Sometimes it can be even less, because even 20 seconds is sometimes little too on the high side. Nothing more than 20 seconds can occur. Maximum is around 20 seconds. So we are going to have about 20 cycles. And if you are having only 20 cycles, can this ever suffer damage? No, because we have huge confinement in the regions where we need. So that's how we should approach the earthquake resistance in buildings, by selecting large enough columns, confining the plastic hinges to beams. Even within beams, we do the detailing like this. Again, on the column, we hate hinges, so we provide confinement. But in the beam also, over 0.6 meters on either side, we have confining reinforcement. So the usual detail I like is H8 at 75 centimeters. H8 at 75 centimeters, irrespective of the requirement of the shear links. Whatever the shear links need space 100, 125, but I still provide 7 over a length of 0.6 meters. Then I provide these additional bars within this region. So that will provide the strength needed within the joint to resist tension. And I have confinement here also. And this type of detailing will do huge ductility to the structure, and the ductile structures can easily withstand earthquakes. So this is how we make reinforced concrete buildings in Sri Lanka earthquake resistant. And sometimes you might say, okay, why don't we do some calculations and find something? Because you can never ever consider the total load and designed for an earthquake because the total load can be massive. So how we actually resist earthquakes is not by designing for a force, but by dissipating the energy. To dissipate the energy without suffering any damage, we need huge amount of ductility. So when you are using reinforced concrete, you can see it's very easy to find the reinforcement in a column. But what matters is not your direct calculation. What matters is how much ductility you are providing in the structure, and also how you have assessed the risk of failure. So what is the advantage of providing this kind of reinforcement detail I showed you? Now, you know, these in a 10-story building, first 2 floors can be car parking. So if a car ram onto this column, if it is 500 by 500 or 600 by 600, can anything happen to the column? The answer is no. Column has been you have used C2530 concrete, so that is cylinder strength 25 concrete. You have cured it. You have put some 10% fly ash into it. So finally, the strength of the column can be 45 megapascal one day, and car crash onto this. Car will be a wreck, but building will not feel anything. Very safe. And another day, earthquake strikes. There's huge amount of confinement in the columns. So columns cannot anyway form hinges because columns are bigger than beams. So beams might form 1 or 2 hinges, but it doesn't matter. Why? When you are designing a beam in an earthquake resistant structure, we know there's a possibility for hinges to occur here and here during an earthquake. So what we do is if the hinges form, what happens to the bending moment diagram? Now bending moment diagram comes like this, and it says, okay, now this is beyond this, I am not increasing. So any extra load will come here. So what we do is when you are providing reinforcement, we provide some little extra reinforcement in the beam. The moment you provide some little extra reinforcement in the beam, bottom steel, even if the hinge occurs in the beam, still the beam can never collapse because it has a huge capacity at the most critical section, that is the span section. So when you are detailing, what we do is go for this. When you are detailing the beam, what we do is we use some hanger bars, provide extra reinforcement here, provide extra reinforcement here, but only marginal. Don't provide any extra because there's no point in providing extra. Then we provide extra reinforcement, and here we provide actually extra. So when you need 4 numbers of H20, we might provide 2 H20 plus 2 H24. We'll be a little generous in providing reinforcement because the moment you do this, you can minimize the reinforcement everywhere else except in the span, knowing very well beam is going to fail. If it ever fails, it will fail at the center. Now I am going to provide extra reinforcement to prevent this failure at the center. So this is how you are to look at reinforced concrete design. But I am sure most of you would have mechanically done it without understanding what's going on. So you have a bending moment, you refer a chart or do a calculation, provide the reinforcement, and you provide a little extra. You don't know what's going on in the structure. But this is how the structure is going to behave when it is subject to dynamic loads. Static loads are not important because the dynamic loads are more critical. And so you have to look at the dynamic behavior of the structure and decide how you are going to do the detail. So with that, Bhanuka, shall I stop the lecture? And I can answer whatever the questions in the chat box.
There are several questions.
Yeah, can you read them?
Sure, sir. What will be the adverse effects if rainwater accumulated on fresh concrete and during curing period?
No, there's no effect because what matters is this huge, there will be huge amount of calcium hydroxide produced. So rainwater can have only what you call carbonic acid, and it will be neutralized in no time. Right?
Okay,
So
sir.
there's no acidic effect of rainwater because when rainwater is even good because it has no chlorine. Okay, Bandhu?
Yeah, okay, sir. And also he has asked another question, how can explain it, the minimum time duration to start curing with water after casting?
No, actually the most important thing is we are in a tropical climate. So you have to protect the newly laid concrete from direct sunlight. Because direct sunlight can evaporate the water very fast. And if the water evaporates too fast, you will get plastic shrinkage cracks. So you must make sure either you start concreting around 5 o'clock in the evening so that no direct solar radiation on it. Otherwise, you have to cover it. But after around 15 to 20 hours, you can start curing. Because the moment the water is not absorbed, you can start curing.
Okay, sir.
The maximum duration is 24 hours. Before 24 hours, you must start curing.
Okay, sir.
Basically, before the sun rises next day, you must start curing.
Okay, sir.
Because, the moment sun rises, it's gone. Sunrise means intense solar radiation, around 800 watts per square meter. So if you allow the water to evaporate, very difficult to get it in. So you must ensure whatever the water that you have used in concrete, it remains within concrete. So that's the criteria. So by looking at the climatic conditions, you have to decide when to start curing. But these modern cements, allow you to start curing after 12 hours. Okay, Bandhu?
Okay, sir. And
Right.
the other question is how we can ensure the skin friction of the soil on the pile if we use temporary steel encasement.
Oh, no, you don't have to worry because soil has a habit of settling, recovering. Because, when you do a pile, you use bentonite and you do everything. Skin friction is low in the initial stage. But if you allow 2 months, the soil has the habit of regaining its lost capacities, and then you will find the skin friction is very high. So we don't have to worry about it.
Okay,
We
sir.
can withdraw the casing and soil will automatically do the rest. We don't have to worry about it.
Okay, sir. And again, another participant has shared his experience. He
Yeah.
has experienced some high class bungalow house, 3-story building with basement, where column
Yeah.
sizes are 250 into 100 and 250 into 1000, and long span beam sizes are 300 into 700. In this case,
Yeah.
can we expect hinges from in the beam? Likewise,
No, actually, if it is a 3-story building with such massive columns and beams, hinges will never ever form. You can see it's out of proportion. Is that right? They're massive.
yes.
So if they are massive, the members are massive, then the plastic hinges will not form because the structure itself has a huge capacity. They are like shear walls. 1,000 meters long and millimeters long and 250 wide. It's on the margin of a column. Because anything more, say 1,200 by 250, then it's a wall. It has to be designed like a wall. So nothing can go wrong in that structure.
Okay, sir. And another question, I have seen some column reinforcement details such a way that there are 4 vertical reinforcement in the core of the column. What would be the reason for that?
No, actually, in that case, it's not a detail that we need. But some engineers, due to there are some reasons, like, now you see, let's say you are going to have pre-stress in the beams. So pre-stress can move the column. So one of the things we do is, when you have a 600 by 600 column supporting a massive span, say 20-meter span, using a pre-stress beam. What we do is we put the reinforcement on the edges, but we put another core inside, because what happens is there will be some cracks forming, because when you are doing the pre-stressing, there will be axial shortening. So that will start dragging the column. So in that case, you will have a core where you will have extra capacity. So it may be that type of situation. Otherwise, there is absolutely no reason to provide reinforcement in the core of a column. Okay?
Okay, sir.
Sir, I'm Mangala here. I just want to ask this additional question. I mean, the what you said regarding the reinforcement inside the something like a core of the column. Is there any guideline of calculating that type of thing, or is by just a practice? So
no. It's basically you will look at the axial shortening and what is the moment induced, right?
Okay.
So for that you will provide small diameter bars on the outer.
Okay.
So that the cracks will be distributed, cannot be seen. But if you need any moment capacity, then you will make sure inside the reinforcement inside it can provide the adequate moment capacity. Right? It's a very special case one. The only occur when you do what you call pre-stressing in beams and slabs. You have to be a little careful of this, column being dragged by the pre-stress. So sometimes we don't do pre-stressing around the column, but we do pre-stressing everywhere else, and then we fill the gap with reinforced concrete. So there are so many different techniques, but this is a very special case. There's another question. I saw something just typed.
Yeah.
What is it?
What is the minimum requirement for tie beam sizing for a building with a ground floor plus one floor structure arrangement, where the tie beams are supported?
Actually, tie beam, what you can do is, there's a simple equation to calculate the base shear, right? And base shear means if you consider particular earthquake magnitude, something like, if you are using Australian code, you can say acceleration coefficient of 0.08, which is the value recommended for Sydney. So we can't have any earthquake bigger than the earthquake in Sydney. So we calculate the base shear, and we have to make sure the reinforcement provided can take this base shear. Then there will not be any distinction. That's all. So generally, when you do this calculation, you will find two numbers of 10 millimeter diameters bars in the foundation level is enough. But you can't provide. So you can provide a simple type. No, nothing. The moment you have two numbers of strength, most of the buildings you will find it is sufficient to ensure that the whole foundation moves in one direction during an earthquake, because the whole base shear will be less than the total tensile capacity of all exchange bars, because you will have a number of beams in one direction, another number of beams in the other direction. So my experience is two numbers of exchange is more than enough in a small building, like a 2-story or 3-story house, and I might even use two numbers of H8. Even H8 is enough to make sure the foundation never disintegrates. It's a small building. But in a bigger building, you can calculate the base shear and see how much reinforcement is needed in anyway, in a big building, the most likely case is you will have a ground slab, reinforced concrete ground slab. In such a scenario, say 10-story building, most likely case is even the ground slab will be reinforced concrete, right? So in such a scenario, you might not provide one layer of reinforcement, you might provide 2 layers of reinforcement at the ground slab with small diameter bars. Then you don't have to worry. The whole building will behave as one entity. Is that clear, Bandhuga?
Yes, that is clear.
Yeah, to design the tie beam, you have to look at the base sheet.
Okay, sir.
There's a simple equation that take account of the soil type. That is the early equation. Or otherwise, you can calculate the base shear for Australian code or whatever, Eurocode or whatever the code, and make sure the in one direction base shear can be taken by reinforcement going into tension. That's all.
Okay, sir. And another question is related to tie beams. Don't we consider the differential settlements of foundations when designing a tie beam?
You know, the differential settlements cannot occur. If you properly design the foundation, differential settlements cannot occur. What is the reason? Now, let's say we are in a laterite soil area. We are told, the geotechnical engineer says, okay, you can use 200 kilonewtons per meter square. Now, what is the meaning of this 200 kilonewtons per meter square? When you apply 200 kilonewtons or 20 tons over 1 square meter, the soil is going to have an elastic deformation of 25 millimeters. And you have to say, we are in Sri Lanka. Laterite soil, will it ever settle after that? No. Laterite soil is hugely strong soil. The bearing capacity can be, at ultimate can be 700, 800. Why we apply 200 is to make sure the settlement elastic deformation is 25. So if you do a proper foundation, the differential settlement is 0. But there's a place where the differential settlement can occur, and that is clay sand or sandy clay. It's all clay soils. In such situations, we don't use isolated footing. What we do is we go for inverted T-type foundations placed on ABC fill. And the moment you have such a strong foundation, differential settlements are against you. So you don't have to worry about differential settlements in Sri Lanka if you properly design the structures. Or you have good soil. If you have good soil, no differential settlement. If you have weak soil, we make sure differential settlement is 0 because we put the whole thing on an inverted T. Okay?
Okay, sir.
I'll
That's
show you how
clear.
to do the modeling on method. All those things I can show you. And I shared some set of notes. Those notes have all those calculations because that's a set of notes specifically prepared for foundation. So you could please go through the notes and you can learn a lot on these.
Yes, sir. We have shared it with the group.
With the group, right? So just ask them to go through the notes. Those notes are actually for MSc in geotechnical engineering, and you can learn a lot from those notes. So basically, the ideal is to go through the notes. And in Sri Lanka, you can't have differential settlements if you have properly designed the foundations. If it is even if it is isolated footings on laterite soil, no differential settlement. If it is weak soil, because they can be different settlements, you put the whole thing on inverted very stiff foundation. Then you can't have differential settlements. Is that clear, Manduga?
Yes, sir. That's clear. Seems like the questions are over for now, sir.
Yeah. Okay. So then we'll wind up.
Okay, sir. And I would like to. Okay, someone has asked to share the notes. Actually, we are sharing the notes in our WhatsApp group. Someone has put the email address. We'll share to that also. Okay.
Yes.
And we are thankful to Professor Tisan Jayasinghe for conducting this lecture series. Actually, this lecture series has become very interesting among practicing engineers. Most of the questions they arise and they are getting cleared on them. So this has become a very interesting lecture series for all practicing engineers. Thank you very much, sir, for sharing your knowledge on that. And also, I would like to thank the chairman, Civil Engineering Sectional Committee, Engineer Mangala Silva, for initiating this timely lecture series for this year. Thank you very much, sir. And also, I would like to thank the ISL Secretariat, IT Department, and the Publicity Department for hosting facilities for this lecture series. And also, more importantly, I would like to thank all the participants. Your enthusiasm and interest on the subject and questions, all these things make this lecture series a success. So our next lecture will be on next Wednesday at 7
That
p.m.
is 20th, is that right? 20th.
Yes, that is 20th. Are we conducting on 27th as well?
Yeah,
we will conduct.
Yeah, 27th. Yeah, I will let you know. So generally, I have kept all Wednesdays free.
Okay.
But
sir.
because this family conference is coming and there are so many things happening,
Yes.
so 27th is also a possibility. But if there's any change, I will inform them.
Okay, sir. Okay.
Right?
And,
but I have put all Wednesdays free generally.
Okay, thank you very much, sir, for that.
I never accept any appointment on Wednesdays.
Okay.
Only during daytime, after 4, no appointment. So generally, I will keep all Wednesdays free so we can continue.
Okay,
thank you very much, sir, for for your dedication. Thank you very much. On behalf of Civil Engineering Sectional Committee, I would like to say thank you again. Thank you, Professor, and thank you, Bandhuga.
Okay, thank you very much, sir. Thank you.
Yeah, I'm going to leave. Okay, thank you very much.
Okay, thank you.
Thank you, sir. Thank you.